Let's take a look at dimensionality reduction. First thing that we want to take a look is a basic introduction of why do we need dimensionality reduction and some very famous theory about the curse of dimensionality. In this chapter, we really want to discuss a couple of topics. One of them is the curse of dimensionality, and then second thing is the major dimensionality reduction methodologies, including PCA, kernel PCA, and something called LLE. Let's take a look at this example. Recall that for the MNIST dataset, we studied the pixel importance, right? So we mentioned that in this graph for all the numbers, handwritten numbers, those images, um, it turns out to be the case that this area that is more brighter are more important, just because majority of handwritten turns out to be the center of the image. And as a result, what will happen, right? If for each small square, if we consider that to be a pixel, then it turns out to be the outside of this image, although dark areas are not as important as what's happening in the middle. And also, if you combine multiple pixels together at the end, you won't lose much information. So recall that when we did this, right, each pixel turns out to be one feature or one dimension that we studied. So if you could combine multiple features, meanwhile it doesn't lose much information, then that's ideal because your calculation would not as computationally intensive as it could have been. So just remember, there's a chance that you would be able to reduce the feature dimensions by combining multiple um, dimensions. So in this part, we also call it as feature engineering and also dimensionality reduction. So let's take a look at the example that let's think through a little bit more from theoretical perspective, right? So this picture really shows you that, you would be able to kind of picture what's happening in three-dimensional space, maybe even one more fourth-dimensional space. Beyond fourth-dimensional space, it's very difficult for you to visually picture what it look like. But nevertheless, let's think about some theory here. Let's say if you pick a random point you are in a unit square in two-dimensional space, it will have only about 0.4% chance of being located less than 0.001 from the border. In other words, it is very unlikely that a random point will be extreme along any dimension. So it's kind of evenly distributed in the square, and you just don't see it's going to be close to the border. However, for a 10,000 dimensional unit hypercube, if you pick another point, this probability is greater than 99.99%. What does that mean? That means in the higher dimensional space, all the points, not all the points, but at least most of the points are very close to the border. That is one of the feature of higher dimensional in higher dimensional in one of the features of the higher dimensional images or graphs or space. So let's look at another interesting property. If you pick 2 points in a unit square, the distance between these 2 points would be roughly 0.9, 0.52. So all of these numbers are based on some sort of research. We're actually not going to elaborate as much, but the reason that we want to see this is really to give you a motivation or discussion of the need of dimensionality reduction. If you pick 2 points in a 3D cube, the average distance would be roughly 0.66. How about 1 million dimensional space? The average distance will be roughly 408.25. What does this show us? It actually tells us that in a higher dimensional space, when you pick 2 points, they kind of far away, right? Much further away than in a lower dimensional space. So it, just because they're far away, and why would that happen? It's only just because in higher dimensional space you would have more space, so that even you randomly pick 2 points, they're really far away, and then the points that located would be very sparse. Conceptually, that would be what's going to happen. What's going to happen? All the points are very sparse, and then if you build your machine learning algorithm, what happens is you got to pick some sort of samples from the space so that you're able to build your model, right? So since they're really further away and a lot of them are located near the border of the unit square in higher dimensional space, so that when you pick a sample, the sample turns out to be somewhat sparse, and the points are further away. With that being said, once you train your model, you get a new instance. The chance in a high dimensional space would be that the chance that the model can do a good job on the prediction sample would be really low. If you recall the generalizability of machine learning algorithms, so that what's happening is it's not going to do a good job on the prediction. Essentially says the general algorithm would tend to be locating on the right hand side of the curve we talked about in the bias and variance trade-off. As a result, it's going to be likely to be overfitting your data. So in higher dimensional space, so here is really the conclusion. In higher dimensional space, the chance of overfitting becomes higher. Okay. So one potential solution for this would be you have to increase the size of the training instances. However, it's very difficult to do this once the dimensionality becomes really high, just because the number of training instances required to reach a given density grows exponentially with the number of dimensions. In a higher dimensional space, we want to increase the number of instances or observations in our training sample to compensate the fact that they are so sparse, or the points are so sparse and far away. If we have more observations with the hope that they're closer to each other, not as sparse as it could be, then we would be able to build our training algorithm. However, just because of the fact that we're not able to do that, just because you need a lot of, in practice, you need a lot of more observations than you actually have, then you're not able to continue to expand your number of observations or the size of training instances by doing that in higher dimensional space. So as a solution, that is the introduction reason. That's the reason of dimensionality reduction, which would be helpful. In other words, instead of trying to increase the number of instances, we are trying to decrease the number of dimensions of feature space dimensionalities to resolve the issue of the curse of dimensionality. Okay, so let's look at two major dimensionality reduction approach. One of them is called projection. Let's look at the chart on the top left. It's just forget all the black diamond for the time being. Just think about all the blue dots. The blue dots are in a three-dimensional space, just normal three-dimensional space, x1, x2, and x3. They locate somewhere in those in this 3D space. One way that we want to simplify this problem is, let's do a projection onto that plane, which is a gray plane that is defined by those two axes, one of them being this, the other one being this, right? So what happens is, on this hyperplane, if you project this point onto this hyperplane, it will result in this point. Same thing for this point, result in this diamond, so on and so forth. So at the end, if you just look at what's happening on the diamond, what's happening on the hyperplane, or the diamond points, it should look like what we saw on the bottom right hand side, right? So three-dimensional space points are projected to a hyperplane, shows on the two-dimensional space. In a two-dimensional space, it is represented as new axis z1 versus z2 with all the projected points. So conceptually, you're probably thinking that this point is corresponding to this one, and some of those, so that's why it looks like this kind of curve, more like a C, right? So that's one approach, projection, right? We're using three-dimensional to show you that you can project from three-dimension to two-dimension. And in machine learning, you could think about projecting 1000 dimension to 300. That could also happen. Then the question becomes, from 1000 dimension, should we project to 300 or 350 or 550? That comes to the reason that we want to discuss all the dimensionality reduction algorithms to figure out what would be the best way of projection, and also without loss of a lot of variability of your original data. Because if you didn't do that, you're running the risk of losing a bunch of variability in your data. Then it's just the loss of important information, right? So at that point, I want to go back to this graph to see that if you combine a lot of these features together, the dimension that you specified on this chart is not as accurate as it should have been, then you running the opportunity of running the risk of not being able to do a good job on your machine learning algorithm. So in other words, we should figure out what would be the proper dimensionality reduction or proper dimensions that the features should be reduced to in our original dimensionality reduction algorithm. Okay, so let's look at another way to look at this dimensionality reduction. So let's think about this graph on the top left hand. So in this graph, if we just do the same thing as what we just said, let's project onto x1, x2 plane. Then what would happen? All these yellow points would be on the right hand side. These would be overlapped with each other with some yellow, and these would be on the left hand side. That would be exactly what you saw on the bottom right hand side on the left side of this chart. You can see that, okay, yellow are here, all these are kind of overlapping with each other, and this side would be orange and red. This projection, does it help us as much? No, because if you are running some sort of classification or clustering algorithm here on this chart, it's very difficult for you to digest, right? However, there's another way we could think about. So instead of doing projection, what we would do on this classic example is called Swiss roll dataset. You could unroll the Swiss roll dataset. Unroll meaning it's rolled together and then try to unroll it. Just consider that unroll this over to that side and unroll this to this side so that it shows actually as what you saw on the right hand side. This is much easier for you to run any sort of classification algorithm, right? You would be able to easier to differentiate these from the yellow ones. Also differentiate these from the red ones. So that's a different way to think about this problem. So sometimes projection may not work. That comes to that point that we want to discuss something called manifold learning. That's a second approach usually that you should take in dimensionality reduction. One of them is projection, second one is manifold learning. So the Swiss roll example is a 2D manifold. Put simply, it is a 2D manifold is really a 2D shape that can be bent and twisted in a higher dimensional space. Before you unroll, after you unroll, it's a 2D shape. But if you roll them together, it shows in the 3D space. So again, a 2D manifold is a 2D shape that can be bent or twisted in a higher dimensional space. And then many dimensionality reduction algorithms work by modeling the manifold on which the training instance is lying. This is called manifold learning. So in other words, you could do a unrolling so that we can look at it on a 2D space. This manifold learning relies on the manifold assumption, which holds that most real-world higher dimensional datasets lie close to a much lower dimensional manifold. So in a 2D space, in this lower dimensional manifold, you are able to see the relationship clearer and they line close each other. Very often this assumption turns out to be empirically observed, which is good news. So, and we also have this assumption essentially says that the task at hand, classification or regression, will be simpler if expressed in a lower dimensional space of the manifold. So use that Swiss roll as example. You would be able to digest the data much easier in two-dimensional space. However, it may not always work. So let's look at this chart. On the top, essentially says, if you have a three-dimensional space data, and then if you unroll to two-dimensional, you would, once you unroll, you see yellow is on that side, further away from X2 side, and green is on this side. As a result, in the two-dimensional space, you see that green and yellow points are easily to be differentiated by this classification line. That's good news. Essentially says manifold learning is going to work in this example on the top chart. But on the bottom side, let's say in three-dimensional space, because all the points are lying more like this shape, if you actually unroll them, it shows as this on the bottom right. It's much harder for you to understand. Instead of unrolling and do the classification, then you would be better off just by looking at original data. You would be able coming back with this hyperplane, which is x1 equal to 5, to differentiate the green versus the yellow. So the conclusion from this chart is sometimes reducing the dimension or unrolling the original manifold can help you, which is the top two graph. But sometimes in other scenarios, it's not going to help you, which shows on the bottom two charts. So you might be better off just stay with the original dimension. All right, this is really just a high-level introduction of the class of dimensionality. Number one, key takeaways. Number one, in higher dimensional space, points are so sparse, and there's a higher chance that a lot of them actually kind of lines in the border of the higher dimensional space. That is the curse of dimensionality. Number two major methods for dimensionality reduction. One of them is projection. Second one is manifold learning. Okay, I'll stop here and thank you.